Hi everyone. Now I would like to talk about egocentric action recognition by capturing hand-object contact and object state. Egocentric action recognition is the task that understands human actions in first-person view videos. Breakthroughs in deep neural networks led to end-to-end action recognition models that utilize convolutional neural networks and transformers. Improving the performance of egocentric action recognition requires accurately capturing interactions between actors and objects. However, training with only the pair data can often cause them to learn spatio-temporal information irrelevant to actions. This causes the models to not perform as well as they should. As proposed by Gibson's affordance, when we interact with surrounding objects, we perceive the object's state, affect the object with our body, mainly hands, and often change the object's state. For example, open fridge can be viewed as a hand pulling the door of a closed fridge, and the state of the fridge changing to open. Models need to learn the contact between the actor's hands and the objects relevant to the action, and how the object's state changes due to the action. Therefore, we introduce two learning methods that enable end-to-end recognition models to better understand actions by capturing hand-object contact and the resulting object state. Our proposed method consists of two types of learning, hand-object contact learning and object state learning. They are integrated into a normal action learning in the training phase. In the following, we explain them in the learning and inference procedure in detail. For hand-object contact learning, we prepare Video Recognition Model 1, which learns actions from the raw video, and Video Recognition Model 2, which does from the masked video. And they collaboratively learn actions in the manner of deep mutual learning. The masked video contains only the hand-object region information, extracted by a hand-object detector. Thus, Video Recognition Model 1 captures the contact between hand and the object associated with actions, by approximating its predicted action probabilities to those of Video Recognition Model 2. To realize hand-object contact learning, we propose a loss function that minimizes the difference between the predicted action probabilities by Video Recognition Model 1 and 2. To capture object state changes during actions, we define a frame-level object state prediction task. The state of an object is generally described by adjectives. Therefore, we manually annotated the states of an object before and after each action. For example, for the open fridge action, the initial state is closed, and the final state is open, since a closed fridge is opened by the action. If an action does not change the object's state, such as hold spoon, the same adjective is assigned to both the initial and final states. Actions that do not affect the state of an object, such as read recipe and wait, are labeled as none. After that, we automatically generate pseudo-object state distributions corresponding to each video frame. Video Recognition Model 1 learns the frame-by-frame distributions, as well as the video-level actions, so that it captures the object state changes associated with actions. To realize object state learning, we propose a loss function that minimizes the difference between the ground truth object state values and the predicted object state values by Video Recognition Model 1 and 2. In the training phase, Video Recognition Model 1 and Video Recognition Model 2 are optimized collaboratively, in the manner of mini-batch learning. We prepare a mini-batch of videos for Video Recognition Model 1, and then generate masked videos by using a hand-object detector for Video Recognition Model 2. Then, they compute their predictions, and learnable parameters are updated in turn at each iteration. This procedure is iteratively performed until convergence. In the inference phase, we only use Video Recognition 1. It means that models trained with our proposed method can predict action labels from only raw video, just as models trained with pairs of a video and action label in the end-to-end manner. We evaluate the performance of our proposed methods on 3 datasets. We employ slow fast and video swin transformer pre-trained by kinetics in our experiments. The results show that the use of our learning methods mostly improved the overall performance, in different domains and with a range of dataset scales. In addition, they make the models robust for minor classes and unfamiliar scenes. We also evaluated the effectiveness of our methods for models, pre-trained on a large dataset from the same viewpoint and domain. Because the type of dataset used in the pre-training phase greatly affects the performance of recognition models. The results show that our proposed methods are effective, even when the models are pre-trained on a large dataset in the same domain. Models trained with our proposed methods predict actions with only RGB of a video for inference. Therefore, it is appropriate to consider the latest end-to-end models, such as slow fast and video swing transformer, as the baseline models for comparison. On the other hand, we also compare with existing methods, utilizing not only RGB, but also human body motions and active objects. Those tables show performance comparison with them. Models with our proposed methods are comparable or better performance, even though the existing methods utilize the information of human body motions and active objects for inference. We qualitatively evaluated the two proposed methods to better understand their behaviors, by visualizing where is focused upon to recognize actions by models trained on each method. We visualize slow pathway of slow fast using GradCam. The model trained with only action learning reacted strongly to the closed cabinet in the second frame, and thus recognized incorrectly. This shows that the slow fast model cannot adequately capture information relevant to the action in the training phase. On the other hand, when slow fast was trained with our proposed methods, it recognized the action by strongly responding to the region where the left hand contacted the cabinet, and where the cabinet state changed from open to closed during the action. To summarize, our proposed methods help models to classify actions more accurately by focusing on hand-object contact and object state change. Experiments demonstrated that the two proposed methods improved recognition performance in different domains on datasets of various scales. This improved recognition performance, especially for classes with a few instances in the train set, and for unseen data. We also showed that our proposed methods incorporated the relationships among action, hand-object contact, and object state change into models through visualization. Our proposed methods require annotation of an additional adjective label for the datasets. Therefore, in future work, we need to design a method that works in an unsupervised or self-supervised manner. We also found and discuss hand-object contact learning tends to contribute more for slow fast, whereas object state learning contributes more for video swing transformer in our paper. Further analysis of these affinities is required in the future. Thank you so much for your attention.